Well, it's official, folks. Looks like we can start our last class. It's been kind of an interesting adventure. It's been 15 full weeks of lots of random topics, lots of chaotic data, but it's been fun putting it all together, seeing how it all actually starts to connect. The whole course really had a interesting purpose, just about in every single section was related. And what's kind of crazy is we really could have covered a lot of stuff if we, say, had 2 semesters back to back. We could have gone through every topic in the entire book if we wanted to. Statistics is pretty vast. And so if you know you're taking more statistics, the next course would be statistical methods. That's next up, which is kind of doing what we're doing on the first 4 problems here, but it resolves questions of what do you do if there's 2 population means? What do you do if there is a categorical variable with 5 outcomes or 2 categorical variables? The landscape of statistics just keeps on going and going with more and more complicated situations. But these situations are plenty complicated too. We're going to finish off exercise 4, the last inferential statistics one, and then go into the other random topics in these notes. But for the other announcements and reminders, don't forget there's 2 extra credit opportunities on the table. One is for the final exam grade, can full on replace a minimum exam grade if it's higher. Another one is really not exactly extra credit, but it's allowing us to turn in any quiz whatsoever that might have gone late for full credit. And same with MyLab statistics. Anything work you do here, it closes on Monday, but any work you do on any MyLab statistics topic that might have gone past due, you can bring that score back for full credit as well. So quiz number 11 is the last one due. When you go to study for the final exam, there's a couple versions here. Same kind of stuff that we've seen before, but it's updated all the way through the last chapter 15. And this is the real final exam as well. So this is a good one to take a look into. I want to mention, when it comes to writing these final exams, I don't make them too long. I think I said earlier, probably towards the start of the week, it's going to be about the same length as this one here. So expect somewhere between 7 to 9 problems, probably closer around 8. But I can't ask every single question. And this is where these documents actually can become really tricky. Last time I taught this class, I didn't ask a chapter 7 question because I didn't want the exam to get too long. So I just randomly omitted that topic. But for this semester's final exam, just as a hint, and so that this document doesn't cause more harm than good, expect a chapter 7 question on the final. So I think it'll be a good idea we do at least one of those today. That's in the review document right up above. Well, other comments to mention to help prepare for the final exam is take a look over your old exam 1, 2, and 3. Look at the notes that you brought to those exams and let that inform you on what you want to put on your 2 pages of notes. It's a good idea to start putting that together sooner. The top of this review here is going to give the formulas we're going to need for any statistical inference problem that does come up. And then the rest of your exams can take care of, say, the other half of the notes. So get started on that quick. Make sure if your calculator is one that charges that it's fully charged, or if it needs new batteries, make sure you replace those batteries. I'll be bringing some spares as usual, but make sure your calculator is in order. Don't forget it, because changing a calculator is just one weird random extra stress that you don't want to deal with on a final. And also, out of the sake of fairness, not everyone does their best work at 8 p.m., but that's the official time of the final exam. I've requested an additional time. You're allowed to show up at 5:30 as well in this same exact room. So if you feel like you're going to work better at that hour, or if it just fits in your schedule better, I'll be available at that time for the final. You'd have to show up at 5:30, a little bit earlier, say 5 to 10 minutes earlier is a good idea just to get settled in. So I can't give exams where you show up at, say, like 6:30 or something like that. It has to be at the start point, since I can't allow the exam to overlap into starting on the next set. I'll also be here at 8 to 10 p.m. If that's just the time that works for you. I'll be here. Even if it's just one student, I'll be here for that entire time. If nobody shows up, then I'm probably going to leave after a while, but I'll definitely wait after just in case. Well, any last questions or comments at all, folks, about the final exam, any of the announcements? Okay, well, let's get into our review so we can make as much segue or headway into this as possible. Anything we don't finish off, I'll finalize on Friday after doing the grading and get it uploaded back here. So we are on the last statistical inference problem, confidence interval for categorical data. Let's remind ourselves what this is about. This is about a pretty awful looking condition in children who are diagnosed with arterial ischemic stroke. In this problem, they have 59 of such children. 25 are classified or diagnosed with delayed perinatal stroke. They also have that condition at the same time. And so the parameter P is the percentage of delayed perinatal stroke among all children in the population, all children with this condition, arterial ischemic stroke and porencephaly, that's a tricky word there. So it's a confidence interval problem, so we didn't have to state hypotheses. It wouldn't have made sense. We're doing this at 99% confidence. So this screenshot is here just as a reminder, that's just a table lookup. Good table to have ready to go in the notes. Critical number is 2.58. And next thing we're going to calculate is the standard error of p hat. So throwing in our values, one thing we didn't calculate was p hat itself. It's looking at us right up here, but let's write this in. P hat is 25 successes out of a sample size of 59. Let's throw this in the calculator. 25 divided by 59. So it's this value here. If we were doing this one really carefully as, say, a MyLab statistics problem, you do need a lot of accuracy. Even when they say round to 4 decimal places, you should go for 5 or 6. Let's go for a highly accurate answer, as if you were doing it in MyLab statistics. If you're doing this on an exam, though, and you just rounded this to 4 decimal places, I'm not super critical on the rounding. If I see the right process, that's the most important thing to me. But just for the sake of the MyLab homework, let's put in 0.423729. So that's the value p hat that goes here. 0.423729, sensing that squared symbol is not long enough. 1 minus the same value, 0.423729. Divide by the sample size, which is 59. And any mistake you might have made on the calculator, you still get the massive partial credit. Just as another reminder, by putting this down on paper somewhere gets you lots of credit. So let's throw this into the calculator, get an output. Standard error p hat. Calculator shortcuts are a good idea here too. It's second in power 2, and this is the highly encouraged shortcut for the sake of accuracy and speed. Hit up arrow to paste it in after hitting enter. Parenthesis 1 minus. Up arrow again, highlight it, hit enter to paste it back down. Close that parenthesis, and we're doing this to even higher accuracy. Divide by 59. And let me know if you're getting a different value from this quantity here. 0.064, 333 upon rounding. Does that look right to folks so far? Awesome. So that's pretty much the worst part of the computation side. Step 3 was finding standard error. So it looks like step 4 should be compute the interval. It's a confidence interval for a population proportion. So the form that this takes is the statistic p hat. Add or subtract the critical number z star multiplied by the standard error we just found. So that's the entire interval. Let's put it down on paper here. So first part, p hat, is 0.423729. Next part is add or subtract, then throw in critical number z star from step 2, 2.58. Multiply that number by standard error we found in step 3, 0.064, excuse me, 333. Then we're just going to throw this in the calculator, and we have the parameter p contained in the middle. So 0.423729, go minus first, 2.58, 0.064, 333. Okay, so here's what I have for the lower bound. I would say this one is a good one to round now back down to just 4 decimal places. It's 0.2577 upon rounding. On the upper bound, up arrow to copy in that last equation, just flip the sign in the middle to positive right here. So now we have the upper bound for the confidence interval. To 4 decimal places again, it's 0.5897. So we did it. That unknown population proportion p here of this particular kind of stroke among all children with that particular condition, that's a wide margin of error. It's between about 26% and 59%. But if some pediatrician specializes in this condition, maybe they're about to open a practice, it gives them some expectations of how often they're going to see this kind of condition amongst this population of children, the ones that have that condition. We said percentage over here, so if you want, you can convert this to a percentage. Let's make that happen on this problem. I don't know if that was just me, but that seems like the lights are flickering. 25.77% is less than p as a percentage, which is less than 58.97%. I'll use the percentage when we go down to the practical conclusion next. So let me take a quick screenshot. Our conclusion is just knowing exactly what the parameter p is and looking into the form of the interval. Also, we need to recall what level of confidence we had. But this takes us to the final step, step 5. Let's say for this, provide a practical conclusion using the context. So that's our last portion to get through. For the practical conclusion using the context, really not too much when it comes to a confidence interval. We have to state the level of confidence like we mentioned. So we were at a 99% confidence interval, stated somewhere at the very top up here, or also indicated here when we selected that. So let's begin by saying, with 99% confidence, okay, so now we have full transparency. We know the level of confidence of the interval is very high. Part of the reason why the margin of error is so wide, the interval is a very wide one. Now we're just reading out this entire triple-sided inequality, starting with the thing in the middle. The population percentage of delayed perinatal stroke among all children with, and if you just said these conditions, I would say that's probably appropriate on this as a final exam. It's a pretty technical medical condition that they're talking about, kind of a constellation of conditions that it even sounds like. So you're mentioning you're not talking about, say, necessarily every condition, one with a specific set of conditions. So any paraphrasing you do is appropriate if it's within reason. It's always kind of a hard judgment call to make. So on the careful side, let's write this in and be highly specific. Among all children with arterial ischemic stroke and porencephaly, so that percentage of the delayed stroke is between 25.77% and 58.97%. So at this stage, the problem is over right at that step. Well, any questions at all, folks, running through this full problem here? Yeah. Oh, I see. Delayed perinatal stroke. And I wouldn't say it's a being a downer. This is really serious data. So it's kind of cool to know more about it too. Notice that there was perinatal strokes. That must have been right after birth, wouldn't it? Delayed, yeah, that is really a downer because delayed starts to sound like we knew our kid had a condition, arterial ischemic stroke and porencephaly. We thought we were fine because this didn't happen, but it did. Delayed perinatal stroke occurred. That was the success. The other one was childhood stroke, which is probably even worse because that sounds like maybe a toddler or somewhere down the line, 5-year-old or something like that. But we were looking at, and I didn't know about that, 28 days later, you're saying for delayed, typically. Gotcha. So yeah, thanks for mentioning that. That gives us a better feel for what's going on with this kind of problem. So if you're getting into the medical sciences, sometimes it's pretty gnarly work like this. I don't know how the healthcare professionals do it, honestly. They have to have a way of just compartmentalizing the really awful things they see in their job to still stay professional. Probably takes a certain person to do that well. I don't know if I could. Other questions or comments at the moment? Okay, well, we got through all the statistical inference problems so far. Congratulations on getting through them. We started our review looking into the hardest stuff at the start of the review, but I think that makes sense because seeing all of this at once gives us a good feel for what all the formulas are going to look like, what all the scenarios are. So when you go to write out your page of notes, thanks for that very helpful suggestion at the class at the end of the night. The titles for what the name of the test is and for what the data is at the very top. And this is a great way to organize your note card. Categorical data is a hypothesis test, goes a certain way. Confidence intervals for quantitative data has a certain flow and a certain process. And likewise, hypothesis for quantitative is what we finished last class. It has a certain flow as well. And we just did a confidence interval for categorical data. They have very similar things. The structures look similar, but the actual details have some variations to look into. When you see a random question like this, first decide, are they asking you to do the confidence interval or hypothesis test? Then decide, is this data categorical? If it's going to be categorical, if you can't find any units here other than a notion of successes versus failures, or it'll be quantitative, like in this problem, and you'll know right away because they're going to throw in means and averages at you, or means and standard deviations at you, and that will tell you you're on this side of the analysis. Well, for the next set of problems, here's the other half of the review, other review problems, the other stuff we did throughout the semester. There's one problem, like I mentioned before, that's on the sample final exam, the real final exam. Let me say that better. There's one problem that's not on that real final exam that is on our final exam, the chapter 7 question. So I felt like that's the next best thing to take a look at, just so we can ensure we don't run out of time. Does that sound all right to folks? Chapter 7 next? Okay, let's dive into that one. So
Linear regression stuff.
yeah, exactly. That's going to be this problem number 3 down here. I decided not to ask it last semester, but this semester it looks like it fits in. So we looked at these data a little bit. This was a quiz, but this is a quiz in chapter 6. So all we had was the correlation coefficient. We couldn't do the full problem like we see here. So it's slightly familiar. It says a study was conducted to analyze the impact of different factors on the amount of time it takes for employees at a certain company to complete a project. This one is made up data, but seems like a kind of a realistic scenario. We're told a simple random sample of size 10 is selected from this company, and the number of days it took each employee to complete a project, along with the experience in years, is given below. And this looks like it tells a kind of story. If you look at, say, the scatter plot, experience in years is the explanatory variable on the horizontal axis. And it looks like days to complete the project is higher for employees with low level of experience. The higher the experience, less days to complete. Except for this one guy. There's this one person with 6 years of experience that completed the project in 24 days. Maybe that's workplace apathy, or maybe he's just such an expert that he's become a perfectionist and it just takes a while to get through the project. Who knows what's really going on? But this point right here stands out as an outlier for sure on these data. It says treat experience as explanatory, days to complete as the response. And first question is right out of the gate, calculate the least squares regression line. Add a rough sketch of this line to the scatter plot above. So here's my rough sketch. Kind of hard to get it in there perfectly because the outlier does influence the line. But if I had to guess, it's possibly something a bit like this. Maybe move it around and such. As long as the line seems to be about what I would expect for regression analysis, this is automatically full credit. If your line goes like this, you could lose some points for that. It's not modeling anything well if you go in that direction. If your line goes like this, that's the picture for no relationship. So it wouldn't quite fit this picture either. So I'll go again for just a generic line that looks about like that. Okay, now we have to put the data inside the calculator. Hit the stat key, hit enter right away on edit. Wipe out anything you don't need by hitting clear and enter with L1 selected. And now we'll get quiet. I'll enter these in column-wise. Yeah, it is. So the next thing we want to go into is, it has been a while. I think it's under the stat key is what's next. And you want to go to calculate an option down there. Anyone need any additional time importing data? Okay, glad I'm reviewing this one. After you haven't done something for weeks, or in this case, it might be months, it gets a little foggy. So hit the stat key, move over to calculate. I think this is starting to feel more familiar. Option 4 works, but our author writes the equation in a slightly different way. So we did option 8 often just to match it up. So under linear regression right here, hit enter. It should say L1, L2. So be sure to change it if it's different. Nothing in frequency list. I don't even know what store regression equation would do. I've never done that. So leave all those blank. And here's all the information we need. The equation is y equals a plus bx, but we're just substituting in the values for both a and the values for b. It says round to 2 decimal places. So here's our line, building it from scratch here. We often call it y hat to mention these are predicted values from the model. For a, it's going to be 19.39 rounding. Then the slope is negative, so go minus 0.75 x. And we've got it. The y hat is telling us the predicted number of days completed for x, which is the experience in years. The experience is the explanatory variable. Days to complete the project is the response variable. And that's how all this information is connecting. This is just the equation for y hat plotted here. So we'll do some other kind of concept questions on this, some computations, and see what we can get out of this.
Now R, that's the correlation coefficient, right?
Exactly, yeah. So if you're asked for this value here, it'd be that one at the very bottom.
If you ever have to, I don't know if you're gonna ask that on the exam, but you'll ask us like the strength of the relationship.
Yeah, exactly. Yeah, and that's a great point to bring up. If that question does come up, you definitely would want to take a look into these notes right here. If you saw this relationship on face value, I think it's reasonable to call it a weak relationship. But now that we've got the correlation coefficient itself, here is a really, really blunt rule of thumb. The rule of thumb is context sensitive, but if you have to put down a rule of thumb, our correlation coefficient is about here, which does speak to it being a weak relationship, like you were saying. We didn't quite get to the moderate, definitely not a strong relationship. But you know, the weakness of this relationship might be because of that one value right there. The outlier is kind of damaging things. It's damaging how high this would have been. Delete that one point, and it might suddenly fly into the moderate range somewhere. We won't do that. We're going to keep the outlier incorporated, but that's an interesting side thought to think about. Other questions at the moment? Okay, here's the tricky concept questions next. Does it make sense to interpret the y-intercept of the least squares regression line? If so, give a practical interpretation using the context, and if it isn't, we have to explain why, which often involves a context as well. But here's the great way to always think about this. In mathematics, no matter if it's statistics or an algebra class, the x-intercept always means x equals 0. But what is x? That's the experience in years, the same as the horizontal axis. Whereas at the same time, days to complete is y, not y hat, because those are the real values, not the predicted ones. So if you set x equal to 0, you mean 0 years of experience. You know, that's reasonable in this problem, 0 years of experience. You could have a brand new employee that's being asked to do this task. And it's also reasonable because a lot of the values are close to 0. We have a 1, 2, 3, for example. If all these values were like 12, 15, 20, 30 years, if there's nothing in the neighborhood of 0 whatsoever, we might have said, no, it doesn't make sense to interpret it because that's extrapolation. The value we get wouldn't really make sense. But 0 is close to these values, particularly with having a 1-year person inside here. It's not too far outside this set. And because having 0 years experience does make sense for this problem, we can interpret it. Does that make sense to folks so far? Okay, a scenario for when it wouldn't make sense is we had one problem that had to deal with scuba diving. X was the dive depth, for example. Y was the number of minutes that you could be left underwater, how long your dive could be. The x-intercept 0 didn't make any sense because that's saying dive into a 0 feet depth of water. That's just an unreasonable thing to ask anyone to do. I think that was an exam question that came up. So for exam 2. So for this problem, 0 years of experience does make sense, and we can say the y-intercept is y hat equals, well, imagine what happens when you do plug in 0 for x. 0 goes literally right here and wipes out the negative 0.75. So y hat becomes 19.39 minus 0.75 times 0 for x. It goes back into that spot again. So the y-intercept is 19.39 days to complete. So we need a practical interpretation using the context, because 0 years does make sense, but the interpretation goes fast. We'll just say for a new employee, that's one with 0 years of experience, for a new employee, it takes a predicted 19.39 days to complete the project. So for a new employee, that was just mentioning how much experience they had. We said 0, which lines up with the x-intercept part. But when we plug in 0, we got 19.39 days to complete. So we just went to this part and said, for a new employee, 19.39 days to complete this project is what we would predict. Well, that's what a y-intercept prediction would look like. When it doesn't make sense, you would just say 0 is unreasonable in this problem for whatever the reason is. Maybe it's physically impossible, like in the diving problem, you can't dive to a depth of 0. But we had another quiz problem, which was the age of, say, how many years old a Corvette was and what its Kelley Blue Book resale value would be. 0 makes sense there because now you're just talking about a brand new Corvette you drove off the lot, and Kelley Blue Book will give you a value for that. It's going to be shocking how much it got marked down. So these are all just purely context driven when it comes to y-intercept. For the slope, this is just a process, and it always makes sense to interpret the slope if it made sense to construct the line in the very first place. Any questions at all, folks, before we move over to the slope side? Okay, there's lots of things we can look at when we're trying to conceptualize how to think about the slope. Let's just do one big screenshot here. Okay, so as far as the slope goes, the slope is that quantity right there, multiplying x. We observe it's negative because the line is going downwards. So let's start by just writing out b, or you could just say in ordinary words, slope. B equals, or slope equals. It's kind of odd because we always make a fraction out of this, no matter what the number is. So it's negative 0.75 divided by 1, and it's a bona fide fraction now. And here's the next interesting part about slope. The mantra about slope is that it's rise over run. The rise is actually a sink, it's going down. But the rise over run mentions that we're talking about units, days to complete. Always is the unit of the numerator, so negative 0.75 days to complete is the new unit above. So that's the rise factor going down 0.75. For each additional year, that's the run. So if I move right by 1, I go down by 0.75, and it'll be 1 year of experience. So no matter how funky the data looks, no matter how weird the situation is, the unit that goes up above is always unit for response y variable. And the unit for the denominator is always the unit for explanatory x variable. And all we've done so far is we wrote out the slope with units, but what we wanted was the practical interpretation. So we have to give a practical interpretation. Forgot to say here, using the context. Doesn't hurt to bake that in, just to emphasize. Using context. So we read this out, not too different from how you might read out a confidence interval result or the result of a hypothesis test giving a practical interpretation. We look at the numerator denominator, we think about the problem, and we just say, well, the slope says, we'll start with the bottom. For each additional year of experience, it's a comma, the y hat value, the expected time to complete the project, it goes down. We see it going down on the graph, but also from the negative sign, goes down by 0.75 days. So by 0.75 days, time to complete the project. This is all context for the response variable. Additional year of experience. This is context for the explanatory variable, mentioning the denominator. And the last bit about this is we said goes down specifically because the slope is negative, that negative 0.75 there. So that's the writing out the context for this kind of situation. It always goes the same way, but it's kind of tricky to put it all together because there's lots of stuff when it's two dimensions, an x variable, a y variable, being explanatory and response, giving you a horizontal axis and a vertical axis. That's just lots to put together when you're also thinking about rise over run at the same exact time. So this is a pretty good idea or structure to have ready to go in your notes, just as a process for putting this all together. Well, any last questions at all, folks? Getting the interpretation down for the slope? Okay, problems are kind of mixed up on this. It's like we did the easy problem, get the calculator output, and now we're doing all the hard questions right after, the practical interpretations. But from here on out, it gets a lot nicer. Let's use this as a model. We have a couple more questions to look into, but both of those questions are going to be based off of that regression line model down below. So part D asks next, what is the predicted number of days to complete the project for an employee that has 6 years of experience? Well, 6 years of experience is the explanatory variable. So they're mentioning X. They just want to know predicted number of days to complete the project. But that's the y hat value. That's what it's giving us. So this one is a calculator job. We go y hat equals 19.39 minus 0.75 times the 6 for the 6 years of experience goes in for X. Now go back to the calculator and just crank it out. 19.39 minus 0.75 times 6 gives us 14.89 days. We did even more tricky stuff than what we're seeing here on the notes. There's also stuff that we did back when we were in chapter 7 dealing with, say, the residual, determining if the observed value should be larger or smaller based on the residual. But I'm going to keep it about like this for the real exam. The residuals are important information, but we really kind of hammered it out on the MyLab statistics side in the lecture notes. So the real exam question is going to be more similar to this. One last question to take a look into, though. Explain why we cannot use the least squares regression line to find the predicted number of days to complete the project for an employee that has 15 years of experience. That's a weird statement because you might think to yourself, we can just put 15 in for X, and you get 8.14 days. So there's something else going on about this problem. It's not about being able to physically calculate it. We can definitely do that. But we have to return to the original context and look at the data again. We're trying to make a prediction based off 15 years. So let's scroll up again and look at this workforce. Kind of says something about the job. There's possibly high turnover here. There's only one employee at 7 years of experience, 6 years, 4 years, 5 years. Looks like most of the employees are below 4 years of experience, the majority of them. So if you're trying to put 15 years on this graph, well, the line doesn't extend beyond 7. That's some true extrapolation this time. 0 years of experience, that's not a big deal if we're right next to a neighbor value. But if we're more than double the highest value of the data set, and there are good rules of thumbs for this, but it'll be blatantly obvious, like in this case, 15 years is just way outside the range of data. So we can say, just as a quick wrap up, this is extrapolation since the max for the explanatory variable which is data in years of experience, that's why we refer to just the explanatory variable, is 7 years. So this means the predicted value can not be trusted. Well, we did it, folks. This is the complete run through of this problem. Again, we saw this as a quiz where the major thing was just the correlation coefficient. But any last questions at all getting through this one? Okay, so expect something like this on the real final exam. Same kind of things we'll be doing, same kind of practical interpretations, but just a different context. And for the rest of the notes, let's see if we can cherry pick what we'd like to do next. I have a normal distribution problem using inverse norm, normal CDF. So normal distribution, or I have a z-score formula problem. This one's pretty quick. Or I have a 1.5 IQR rule of thumb with a box plot problem. This one's probably the longer one. So what sounds fun to folks? Box plot, normal distribution, z-score.
Could we do the z-score one?
Yeah, absolutely. Good call. That's a great call because it's also a short question. So we'll definitely have time to do another one. So this one's kind of a weird made up scenario as well. It says the technology committee at a college has stated that
I have one more question. Does this one relates to which chapter? It's just how I'm like organizing my notes.
Oh, good call. So this one is chapter 5. And it's really specifically section 5.1. That's a good call. Let me put this on here as well. Section 5.1. When I go to finalize these notes, I think I'm going to duplicate that idea. I'm going to put the sections on each one of these problems. I think that's a great idea. Other questions at the moment? Okay, thanks for suggesting this one. So it says, technology committee at a college stated the average time spent by students per lab visit has increased, and the increase supports the need for increased lab fees. this is probably the administration bullying the technology committee into seeing if they can increase the lab fees. To substantiate this claim, the committee randomly samples 12 student lab visits, notes the amount of time spent using the computer. So they randomly looked into 12 student visits into the computer lab, and these are minutes spent working. I don't know how realistic this might be in real life. I think a lot of people just pop in and leave after a couple minutes checking the email. But one student was there for 74 minutes. Other student was in there for 73 minutes. There's some high-end values. A 38-minute was a quicker one. So first thing we're going to do on this is get the sample statistics. So sample mean, sample standard deviation is up next. But that means it's just like the last problem we went through. We're just going to throw this into the calculator and get some values. So start off just like before, hit stat key, enter. I'm going to wipe out everything so that there's no distractions. Okay, I'll go column wise for the data. 5274. Okay, so I now have 12 observations. That looks about right. Let me know if you're getting a different output. Next step, after you have the data in, whether it's regressional analysis like we just did or summary statistics, hit the stat key, go over to calculate. But this time it's option 1 for one variable statistics. L1 should appear here, then just jam the enter key a bunch. And these are the values we should be getting. It says round values to 2 decimal places for these data. Does it look okay to folks so far? Okay, no harm if you decide to use X bar, but our textbook has made the decision sample mean is Y bar. So I'll call it Y bar equals 62.42 minutes. The sample standard deviation S, we've almost always made a big deal out of this. Make sure you go for SX by the red dot, not the one below. The sigma is if we had a population. And it would be a population if they close down the lab and there's never any more lab visits, and these are the only ones they cared about. But that's not realistic to this problem. It's just a sample. So 15.26 minutes for that standard deviation. So next we're calculating the z-score for an observation where someone showed up for just 8 minutes of computer use. That's going to be a very negative z-score because the mean is 62 minutes. And the standard deviation is pretty decently sized, but it's kind of small relative to the mean as well. So really, this is just like calculating a test statistic when we were doing hypothesis testing. We'll call this z equals, and the only difference is I'm putting an observation y here rather than a statistic. Over here, we're putting in y bar. We're calculating the distance from observation to the mean in terms of standard deviations. This part is always a standard deviation. Even if we put in a standard error, that's just meant to be the approximate standard deviation. So it always has the same kind of object feel, no matter how we calculate the z-score. The observation y is just the 8 minutes the problem gave us. So it's going to be 8 minutes minus 62.42 divided by 15.26. So next up, I guess we don't need a fraction bar at that stage. We're just going to get a number. Easy calculator mistake to make is forgetting the parentheses around your entire numerator. So again, if it's on paper, that's insurance against that kind of mistake. My 62.42 divide by 15. Oh, and I forgot the division. Divide by 15.26. And, I thought it was going to come out bigger, but that is still pretty huge in terms of standard deviations. Over 3 standard deviations is highly unusual. So negative 3 point, it didn't say what to round to, so let's go for just a generic 4 decimal places. Negative 3.5662. Sorry for forgetting to say what to round to on a lot of these problems. I try to be a little bit more careful with that on a real exam, but I think this came up as a question as well on last day's class. There's just no information on rounding. You're allowed to do what's sensible. 2 decimal places or 4 decimal places would be pretty standard in most questions. Well, that's how part B goes, just a generic compute a z-score type problem. And this one is the same, except it's in reverse. This one is the equation solving kind of problem. How many minutes of lab use, so this is a y value we're solving for, corresponds to a z-score when that z-score is 2.58. So the way you get through this problem is, first copy down the information, z equals 2.58, 85 rather. Notice that the z-score is positive. That means the number of minutes is going to be well above the sample mean. So this is someone who's probably in the lab for over 2 hours for this one. The next strategy is just put in the whole formula for z that you see up here. Substitute in y minus y bar, divide by s. Equals 2.85. So the question is how many minutes? Once again, it's the unknown this time, so we'll solve for y. Next step, just plug in the information we have. We know what s and y bar are. So this turns into y minus 62.42. Divide by s, which was 15.26. Equals 2.85. So we have to do next an equation solving on this one. I want to show you a couple strategies for getting through this. One strategy is the pure calculator approach. Some people like to just think of it in these terms, so I'll show how to do that. My next approach is going to be just kind of like a purely algebraic approach, like if you're in an algebra class. So going the calculator route, first copy this in, 2.85. What you want to immediately do is multiply by 15.26. So times 15.26. Whatever the denominator is, just multiply it right away. You'll get a number out. Then immediately add 62.42 plus 62.42. And that does the job. That's the solution, kind of in one step, practically, through the calculator. So let me put this down as a screenshot, just as one way to think about it. If you go that route, you have the solution. Y is 105 point, let's go for 2 decimal places, 91 minutes. So the first step is, let me make sure this really shows up. I think that's as best as we can do. Multiply by s. So do that multiplication there. The next step is add y bar, and the value that's given right here was just the value of z that they provided at the start of the problem. So if this makes sense to you, this is a clean way to get to the kind of through the problem every single time it comes up. If this seems kind of vague, here's the algebraic approach. Let me recopy the equation over here. Y minus 62.42, 15.26 equals 2.85. To solve this kind of equation, everyone hates denominators, so the first thing you would do is clear it. You can multiply the right-hand side by 15.26. You just have to make sure to multiply the left-hand side by that same value. And you can visualize that as a 15.26 over 1, which is helpful because we can recall from the land of fractions that you can cancel the same value from a numerator into a denominator, even across to a second fraction. So you get the 2.85 times 15.26. Now it's y minus 62.42 equals, but hey, that's exactly what we did right here. So we have the value 43.491. Then the next step is, once your equation looks like this, just like over here, this was a division by 15.26, so we did the reverse thing. We multiplied by 15.26. Likewise over here, this is a subtraction by 62.42. So we do the reverse operation, add 62.42. A big bar like this is just saying tally both sides of the equation. These are like terms adding up to 0. So y is just 43.491 plus 62.42. That's what we did right here. It just doesn't look like it exactly. A and S is referring to 43.491. So 43.491 plus the 62.42 gives us something that doesn't look quite right. Let me try again. 43 point, that's what I forgot, 491 plus 62.42 gives us the value 105.911. So either way we look at it, this is the solution to this kind of reverse problem now. We did it. This one is kind of annoying in a certain sense because part C is an equation solving, which feels like it's kind of leaving statistics in a certain sense. But part B is actually a super important problem because it really is all you're doing in a hypothesis test every single time you do a test statistic. You either divide by the true standard deviation, categorical data, or a standard error for quantitative data. Well, any last questions at all, folks, before we pick out a next problem? Okay, it's down to just 2. I'll let anyone in class choose the next direction to go. Should we do a normal distribution type problem, inverse norm, normal CDF, or should we do a box plot type problem instead? Good call. I think this is the one we have time to actually complete in time. The box plot one we might run out of time on. So we'll make this one the last problem for the day, and I will come back to these notes and fill out the box plot problem when it's on Friday. I'll upload those after grading on Friday. So let's see what's going on here. Researchers are interested in the length of a particular type of bone in a population of deer. Yeah. Oh, thanks for reminding me. This would be still chapter 5, but more specifically, this one is in 5.4. So section 5.4. Thanks for reminding me about that again. I seem to have forgotten. Let me put in a reminder of add sections for each problem on the review. That's a really excellent suggestion. Okay, so we're in section 5.4, and this is some really hyper-specific problem. We're not just talking about researchers interested in biology, they're interested in deer. They're not just interested in deer, they're interested in the bones, but only one particular kind. Looks like a made-up problem because they didn't tell us what kind, but that's the context so far. We're told that they measured the bone length in a sample of 200 deer. Hopefully there's an inoffensive way to do that. They found it follows a normal distribution. This is based on their sample data, gave them a nice, roughly symmetric unimodal histogram. It had a mean of 25 centimeters and a standard deviation of 2 centimeters. Now, these values are based on a sample of 200 deer, but this problem is a little bit different. We are now modeling the entire population based upon those values. So they take on a different role. This is now population mean mu is 25 centimeters. We're not saying we know it's 25 centimeters exactly. We're just saying that's our best guess. And if we want to mention the margin of error, that's a confidence interval problem next. So using the best guess, we're going to treat mu as a parameter, even though it's a real approximation. Likewise, this is sigma, the population standard deviation of 2 centimeters. So having those two parameter values down, and the fact they told us this is a normal distribution, everything is really just resolved back in the calculator. We're being asked, what percent of this deer population has a bone of this type that is between 28 and 30 centimeters long? Round to 4 decimal places. So here's the sketch. This is N25 for the mean, 2 for the standard deviation. The horizontal axis is centimeters for the bone length. And the center here is directly 25. Standard deviation is 2, so 2 to the right takes us to the 27. We're asking about 28, so slightly right around here is 28, coming from this statement, and then symmetrically to the left, right about here is 30. In terms of centimeters, we said between 30 and 28. So this area right here answers the question of the percent we expect to have that length for that bone. Anyone recall what calculator function we need in this scenario?
The numbers don't make sense to me on that.
Oh yeah, me neither. So I did 28 and 30. I'm not sure why I put a 30 on that. Thanks for spotting that. I'm gonna chalk that up to just a random micro sleep hallucination. To the right of 28 is 30. Should have been right about here. Thanks for spotting that. It looked right when I wrote it in, but not when we looked at it a little bit closer. So we need that area. I know getting it right on the graph is important because it was looking like, say, 70% of the area based on my other graph. Might have convinced myself that I have the wrong value, even if we do it correctly. Well, to get that area, the correct picture there, anyone recall the correct function on the calculator for this one? Yeah, absolutely. Hit second bars. Normal CDF gives us this right area, so let's write it here. Use normal CDF. Think in terms of CDF as giving you the area or the percent. So hit enter there. It's going to ask for a lower bound, but that's just 28 in this problem. So that's input 1. The upper bound is 30, where the area is cut off. And mu and sigma we have already analyzed in the problem. So go from 28 to 30. Mu is 25. And sigma is 2. So hit enter on all that. And this is, well, it's not a percent. This is a proportion of the area under the curve. If you gave me this number, 0.0606, that would be all right with me. But it really wants a percent, so let's go times 100. And now my rounding is a little bit off. Usually I would have said round to 2 decimal places, but I said 4 on this one for no apparent reason. Let's do what it says, round to 4 decimal places and go 6.0598. And hey, with the corrected graph, that looks plausible, about 6% of the area under the curve. Well, any questions at all, folks, with the normal CDF process at the moment? Okay, next problem is a little bit different because our area is not something like this in between. It goes off in a direction. It says just longer than 26 centimeters. But it's still a what percent type question, so it's still normal CDF. The graph looks a little different. Let's put in same curve as before, and 25, 2. With 25 at the center, But now the question is longer than 26 centimeters. Standard deviation is 2, so it's going to be pretty close to that 25. Here's the 26. We shade to the right this time, unending. So like before, the lower bound is 26. But the upper bound 2, we don't have an actual number for that. It's really no upper bound. Our calculator cannot deal with infinities, so it's going to be 10 power 99 instead. So hit second vars, back to normal CDF as before. This time the lower bound has gone down to a 26, but the upper bound has blown up to 10 power 99. Same values though for the rest of these, 25 and 2 for mu and sigma. Hitting enter on that gives us about 30%. So multiply it by 100 to get the percent. To 4 decimal places, it's 30.8538. Percent. Again, maybe it doesn't look perfect. To my eye, that looks closer to maybe 40%, but it's meant to just give us a visual to see how to organize the information and put it in the calculator correctly. So nearly there. Looks like just one more part to take a look into. What length describes the 10% of deer that have the shortest bone of this type? Well, there's a pattern. If they're asking what percent or what proportion, usually what percent, it's a normal CDF process. But if they're asking what length, that's a value on the x-axis. This will be use inverse norm, absolutely. So this is the one that's different out of nowhere. We still set up a picture just like before. So here's the normal distribution, slightly better than the last one. This is N25, 2. And it said the 10% of deer that have the shortest bone. Shortest means we're somewhere on the left. Solving for this value x, 10% might be slightly more around here maybe. That 10% is now really critical. 10% describes this area. Area equals, well, we can't put in the percentage, so we put in the decimal number, 0.10. So that's maybe another element that's kind of tricky about inverse norm. Oftentimes the question's phrased as a percentage, but we have to convert it over to a decimal. But either way, this is input 1. Keep in mind that I would say for most of the calculators I've seen in class, most calculators only work on area to the left. So what if you shaded to the right? Just use the fact that the total area is going to add to 1. So if I had 0.10 over here, I would take 1 minus 0.10 and get 0.90 for the area to the left. So if we change the order of that problem, we had some examples in the lecture notes, I think possibly in the exam as well. This is the modification we would have to make. But so in other words, if 0.10 doesn't come out right, take 1 minus 0.10 and you'll probably get the right value. So that's input 1, the area. Now hit second vars, go down to inverse norm, option 3. I wish it said area to the left, but they didn't quite fit that in. 0.10 or just 0.1 will do the job. Parameter we have to reset again to 25 and a 2. So that's your calculator output. Hit enter again, and this is what we get. X will be equal to, and don't make a weird mistake like I did with this graph. X had to be less than 25, so that's our check, which makes us seem plausible. 22.43. So we can say 22.43 centimeters describes well, let's say 22.43 centimeters or shorter describes the 10% with the shortest bone of this type. I would give full credit if you said just 22.43, but it's really about everyone at 22.43 or shorter as well. So saying this or shorter, I mean, it won't give you extra credit points, but that's the best way to say it. And the rest was just to tie in the context, wasn't completely necessary. So that's the important number. Try to convey it with or shorter or greater to really match up the concept. And we went over by a minute. Sorry about that. Kind of lost track on this one. But any last questions at all, folks, before we call it a night today? Okay, well, thanks for all your hard work all semester long, folks. This is not only a tough class, but I feel like, and I made a big deal out of this to the math department, we're doing it at the worst possible time as well for learning. I think a lot of people would have been happier with, say, like a 7 to 8:15 class, which is usually what night classes look like on this campus. But we got through it. For any work that you do, turning in old quizzes, working on MyLab statistics, this will improve your grade, but the final cutoff is going to be Monday, December 15th. And if you have any questions while you're studying for the exam, don't hesitate to reach out. We won't have class next Monday. We'll just be meeting either at 5:30 or 8 p.m. for the last finishing touches of the course. But have a great night, folks. Have a great weekend. Try not to work too hard, and we'll meet one more time.
Thank you.
You bet. Take care.
I just wanted to let you know that I emailed my quiz to you because I wasn't able to bring it in person. I also
Awesome. Thank you
emailed
for
a
that.
previous quiz too. So thank you.
Perfect. Awesome. You bet. Have a good one. You too. Take care.